This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 08. The Rankine cycle. Steam power plants. Very high yield on the PE Mechanical, Thermal, and Fluid Systems exam. Expect 2 or 3 questions. By the end, you'll solve a full Rankine problem in about 6 minutes. Here's the problem. A Rankine cycle with boiler exit at 500 psi absolute and 800 degrees Fahrenheit. Condenser pressure 10 psia. Both pump and turbine isentropic. Find the thermal efficiency and the net specific work. This is the canonical PE-style Rankine question, solvable from the handbook in about 6 minutes once you know the pattern. The setup is the work. The numbers are easy. Concept. A Rankine cycle is 4 devices in closure. Water circulates forever, changing phase as it goes. The pump pushes low-pressure liquid up to high pressure. The work is small, since water is nearly incompressible, but not zero. The boiler adds heat, vaporizing it to high-pressure, high-temperature steam. The turbine expands that steam back to low pressure, where almost all the useful work comes out. The condenser rejects the leftover heat, returning saturated liquid to the pump inlet to repeat. The TS diagram. Temperature vertical, entropy horizontal. 4 states, 2 isobars for the low and high pressures, 2 isentropic legs for the pump and turbine. State 1 is saturated liquid at condenser pressure. State 2 is directly above it, same entropy, higher pressure, the pump exit, nearly coinciding with 1 since the pump is near reversible. State 3 is upper right, superheated steam at high pressure and temperature, reached from 2 by boiler heat. State 4 sits directly below 3, same entropy, since the turbine is isentropic, back at low pressure, usually 2-phase, so wet steam. The enclosed area is the net work per unit mass. Setup. Think device by device. Each device is a steady flow energy balance. Pump work is the enthalpy change 1 to 2 for a nearly incompressible liquid, specific volume times pressure rise. Boiler heat is 2 to 3. Turbine work is the enthalpy drop 3 to 4, where the power comes from. Condenser heat rejection is 4 minus 1. Net work is turbine minus pump work. Efficiency is net work over boiler heat. Memorize this skeleton. Build the variable table. States across the top, condenser out, pump out, boiler out, turbine out. Properties down the side, pressure, temperature, enthalpy, entropy, specific volume, quality. You start with only what's given, 3 pressures and 1 temperature. Every other cell comes from a handbook lookup or a one-line equation. When the last cell is filled, the answer reads off the table. Pattern recognition. Steam power plant or Rankine cycle names it outright, but more often the exam just describes the hardware. Boiler exit at a pressure and temperature, superheated, pin state 3. Condenser pressure or condenser saturation temperature sets states 1 and 4, which share the low pressure isobar. Isentropic turbine efficiency, usually 0.80 to 0.92, is applied after the ideal H4. 3 words flag variance. Regeneration is feed water preheating from extracted steam. Reheat splits the turbine with intermediate reheating. Extraction bleeds steam mid-turbine for process heat. 3 steam tables do 90% of the work. Saturated by temperature, when you're given a saturation temperature. Saturated by pressure, for the condenser state, since condenser pressure is given. Superheated, when you have a pressure and a temperature above saturation, like the boiler exit. SI equivalence exists too. If a value falls between table rows, interpolate enthalpy and entropy together, not separately. They're tied to the same state. Solve. State 1. Saturated liquid at 10 psia. From the saturation by pressure table, read off the 10 psia row to fill column 1. Saturation temperature, enthalpy, specific volume, entropy, and quality 0 at the liquid line. Also jot down HFG and SFG off to the side. State 4 will need them. State 2. The pump raises pressure by 490 psi, but water is nearly incompressible, so enthalpy barely moves. Pump work is VF times the pressure rise. Mind the conversions. 144 square inches per square foot, and 778 foot-pound force per BTU, giving about 1.5 BTU per pound mass. so H2 is 162.7. Entropy is essentially unchanged from state 1. State 3. Superheated steam at 500 psia, 800 degrees. In the superheated table, find the 500 psia subtable and the 800-degree row to fill column 3. And because the turbine is isentropic, S4 equals S3 automatically. Drop that value into column 4 now. One state 4 value locked in for free. State 4. The turbine is isentropic, so S4 equals S3. At 10 psia, compare it to the saturated vapor entropy Sg. S4 is below Sg, so state 4 is two-phase. Quality is S4 minus SF over SFG, about 0.91. Enthalpy is HF plus quality times HFG, giving 1055.2. Column 4 complete. If S4 had exceeded Sg, state 4 would be superheated. Different table. Always phase check first. With the matrix full, the math is trivial. From the enthalpy row, turbine work is H3 minus H4, pump work is H2 minus H1, and net work is the difference, 355.7 BTU per pound mass. Boiler heat input is H3 minus H2. Thermal efficiency is net work over heat input, 0.2846. Just subtraction and division, the payoff of the variable table. Final answers. Thermal efficiency is 28.5%. Net specific work is 355.7 BTU per pound mass. Efficiency is dimensionless and work over mass is energy per mass. Checks out. One pro trick, close the loop. Heat out should equal heat in minus net work, about 894. Compute heat out directly, H4 minus H1, and you should get the same. First law closes, a free 15-second check. Traps. 5 ways this loses points. 1. Don't skip pump work. It's tiny, but distractors include the no pump work answer to catch you. 2. Compare state 4 entropy to the saturated vapor entropy at condenser pressure. Below Sg is two-phase, use quality. Above Sg is superheated. 3. The highest impact trap. If the prompt gives isentropic turbine efficiency A to T, apply it. Actual H4 is H3 minus A to T times the ideal drop. 4. Watch the pump work conversions, 144 and 778. Get sloppy and you're off by 100-fold. 5. Keep the temperature indexed and pressure index saturation tables straight, and don't crosswire under exam pressure. Quick recall. 4 states, 2 isobars, 2 isentropic legs, 4 energy balances. State 1, saturated liquid. State 2, pump adds Vf times delta P. State 3, superheated from the table. State 4, isentropic to condenser pressure. Check quality. Efficiency is turbine minus pump work over boiler heat. That's 80% of the Rankine questions you'll see. Next up, topic 9, the Brayton cycle, the gas turbine cousin of Rankine. Same 4-state logic, but pressure ratio and ideal gas relations instead of steam tables. Before then, try the 3 Rankine problems in the workbook. 1 with reheat, 1 with regeneration, 1 with a non-isentropic turbine. PEPrepengine.com/beta. The Rankine cheat sheet, the worked problem PDF, and a 5-question quiz are attached to this video. If the course helps you, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.